All right, so sorry, starting late, I had a printing problem. So I ran out of time at the end of last lecture talking about the stable matching problem. Which was this problem about matching students to schools. Just to remind you about these preference lists. I'll remind you we were talking about stability, where there is no situation where a switch is going to happen, where x is matched to big X and little y is matched to little y, but x and little y prefer each other to the current matches, right? And I described to you this proposal algorithm, which demonstrates that there always exists a stable matching because it terminates after only n proposals per school in this case, or n plus 1. Let's try that again. Only n plus 1 proposals per school occur. This is where the students are the ones doing the proposing and the schools are the ones deciding whether to keep or swap. And this meant that you only had order n squared proposals overall to actually arrive at the stable matching. And this occurs regardless of what the particular preference lists are. Yes? Now, something I didn't mention to you last time that is kind of interesting is that this particular algorithm leads to, I mean, there may be many stable matchings for a given set of preference lists. And this proposal algorithm yields a matching which is in a certain formal sense optimal for the students and conversely pessimal for the universities. Okay. If you turned it around and had the universities proposing, then the universities would get the optimal outcome and the students would get the pessimal outcome. And I think it's actually kind of remarkable that these big, powerful universities that run the match actually run it so that it's student optimal rather than university optimal. But that is what I hear. I believe the reasoning is that for students, this is really a life-changing outcome, which school they get to, whereas the schools just need to fill their residency slots, and it's not that big a deal whether they get this student or that student. But I'm not in that space. I don't work with the doctors, so I can't really attest to the truth of that. Anyway, this was all deterministic. Why did I teach all of this? So that I could demonstrate a cute trick involving randomization. And in order to do it, I'm going to do something very rare in this class, which is talk about randomizing over inputs. So let's consider what happens when you have random preference lists. Does it still take n squared time to arrive at a stable matching? Or to put it another way, how many proposals will take place before you arrive at a stable matching? Well, here's where we're going to use a trick which we've actually used many times already, but I wanted to take a moment to sort of point at it and say, yes, there's a formal thing here. Even though we talk informally all the time, there is a proper formal underpinning for how we talk. And this is something known as the principle of deferred decisions. And the basic idea is that until you look at something, its original randomness stays. And let me fill in what I mean by that. The scenario that I've given is for random preference lists, right? But now let's think what's going on with the proposal algorithm, right? You take a student, and according to the proposal algorithm, the student proposes to, it's sort of in order of preference to schools, right? Of course, it doesn't propose to schools it's already proposed to, because it knows it got rejected by those, but it continues down its preference list, right? The question is, when you take that next step, what is the next school that it proposes to? Well, the principles of deferred decision says that since you haven't looked yet at the next school in the list, at the moment you look, that's when the randomness resolves. And so you basically say, okay, the next school that they propose to is random among the schools that they haven't proposed to yet, right? And the point is that it's like we're pretending that the randomness is happening now, even though, according to this scenario, all of the randomness was set at the beginning of the experiment, okay? So you can formalize this, right? You can write down lots of conditioning and so on and so forth, but we're not going to take the time to do that in this class, and so I just want to flag that is what's going on, is that we are going to often keep our eyes closed and not look at something until the right moment so that we can then say that at that moment it's as if we're making a random choice, okay? So a student's proposal is random among the unproposed schools. So that certainly seems to simplify the analysis. We don't need to talk at all about the random proposal list. We just say that they make a random choice among the unproposed schools. But this is still messy because we have to keep track of which schools a particular student proposed to. So I'm going to introduce you to another trick that's quite useful, which is the use of stochastic domination as an analytical tool. So, I should also say that this principle of deferred decisions, we used it already in talking about quicksort, right? When we say the pivot that you get is, so we sort of ask, when two elements are separated, what was the pivot that separated them? And then we say, oh, at that moment, we're making a random choice of the pivot, right? Even though that choice was probably made earlier. Okay, so stochastic domination is just another idea to have in our toolkit. We say that X stochastically dominates Y, where X and Y are both random variables. If the probability, if for any bound Z, the probability that X is bigger than Z is greater than the probability that Y is greater than Z. Okay, so whatever threshold you set, X is more likely to pass that threshold than Y. And so the intuition here is that X is bigger than Y. Right? But you can't say that when you're talking about random variables because each of them gets chosen randomly. And so sometimes X may end up less than Y. But for the purposes of a lot of analysis, this is close enough to saying that X is greater than Y. Does that definition make sense? One immediate consequence of stochastic domination is a larger expectation. You can work that out using one of the standard formulas for expectation, but it should not be surprising, because we're just saying that more of the probability mass of X is higher than the corresponding probability mass of Y. Okay. All right, so with this principle of deferred decisions, I'm going to simplify my analysis further. what I'm going to do is, at each step, the student will propose to a uniformly random school. So I'm not going to bother to remember what I proposed to before. I will just propose to a new random school every time. Okay. And again, even in this language, I'm talking about, I'm sort of using the principle of deferred decisions, right? Okay, so I actually have two claims about this. One is that you get the exact same outcome. That when you propose to completely random schools, instead of randomizing over the schools that you actually have not proposed to yet, it doesn't change the outcome. Why? Yes, in the back. So that's an interesting claim. I can certainly see that from the perspective of a particular school, it's going to accept it's going to be with the highest proposal that it received, right? But I think that the order in which those proposals arrive may influence which proposals arrive, because it could change what happens with other schools, and like there's sort of this interplay between different schools' decisions. I'm not sure, but I'd like to make a more direct argument about why this doesn't change the outcome. Yes?
So if a student is proposing to a school again, now the school either said no already, or they said yes, but then they didn't want them. So that if you propose a school again, they're never going to accept it.
Exactly. If you propose a second time, you're just going to get rejected a second time. Just don't bother, right? It doesn't change an outcome, right? You've already been rejected. That's not going to change. Okay. A proposal to a prior proposal is useless. So basically, we have this student proposing to school after school, and we are now just injecting some useless proposals that never are accepted. So you're going to have the same outcome, namely that the first time I pick a school that I haven't, a school that wants me, that'll be where I stop. And it doesn't matter how many times I proposed multiple times to schools that I proposed to before. Okay, so I get exactly the same outcome as from the proposal algorithm, where I only look at schools that I haven't proposed to before. Clear? Okay. The second claim the number of proposals with repeats stochastically dominates the number of proposals without. Anybody justify that claim? Yes? Exactly, right? Essentially, the way I get the proposals without repeats is that I do the proposals with repeats, but then I just throw away all of the repeats. And then I get the proposals without repeats. So basically, I can do this bijection of the sample space, right? Or not a bijection, but an injection of the sample space, right? That for any given outcome with repeats, I can correspond it to an outcome that has no repeats with the same probability. Okay? And so in this one-to-one, in this association, the with repeats is longer, sample point by sample point, and so of course the random variable is larger, or stochastically dominates. Okay? And of course that means that the expected number of proposals with repeats is larger than the expected number of proposals without repeats. So we just need to analyze the expected number of proposals with repeats, and we'll be done. Yes? So we use these two tricks, deferred decisions and stochastic domination, just to simplify the problem that we're analyzing. Okay. So now let's go back to the big picture. When does the whole algorithm finish? Okay. And arguing as we did in the deterministic case, I claim that we are done once every school gets a proposal. Right? We used this argument when we were studying the deterministic case. Right? That basically a school is alone for a while, and then it gets a proposal, and the first proposal it gets, it always accepts, because that's preferable to having no match at all. Right? And after that, it never rejects unless it's replacing. So any school that gets a proposal just has a match forever after. And so once all the schools get a proposal, all the schools have a match, but that means we have a perfect matching, and our analysis showed that this is a stable matching, so we're done. Yes? Okay. So all we need to figure out is how long until every school gets a proposal. Okay? Again, since sort of stepping back, I'm not even going to worry about which student is proposing. It doesn't matter, because whichever student is proposing is just using a random school to propose to. Right? It doesn't matter what the student is. Okay? So we're proposing a random school each time. And we're asking how long till all get proposed. Any thoughts how I can analyze this? I know you've probably forgotten about last lecture already, but yeah? Exactly. This is exactly the coupon collector problem, right? I'm picking a different school each round, and I want to know how long until I get all the schools, right? This is just the coupon collector problem. So helpful that I just happened to introduce that briefly before this exercise. And so we can immediately conclude in order n log n expected proposals. Sorry, proposals, not rounds. So the average case behavior of this algorithm is far better than the worst case behavior of this algorithm. And notice I said average case behavior. That's generally the vocabulary for talking when you're talking about random inputs. Okay? And this actually is why it is often less interesting to talk about random inputs. Right? Random inputs tend to be easier. There are actually a lot of NP-complete problems where if the input is random, it's tractable in expectation. Okay. I think something like Hamiltonian path on a random graph is tractable in expectation. Okay. So since we are pessimists and are worrying about the worst case, assuming random inputs is often taking it too easy. Okay. All right. So that's the stable matching problem, which let me introduce a couple of these ideas. Now we can move on to the next topic unless there are questions. No? Okay. Okay, I mentioned already this notion of sort of optimal and pessible stable matchings. There's a whole literature of study of stable matchings because you can define other kinds of, if you don't want to sort of preference one side or the other, you can talk about various notions of fairness in stable matchings. And this has been worked out in great detail. And you can read a lot about it if you're curious. So what we're going to focus on today is deviations from expectation. Okay. Until now, everything that I've done has analyzed the expected running time or some other expectation associated with an algorithmic problem. But as has already been brought up, sometimes that's not good enough, right? If you have some critical time bound that you have to meet, then it's important for you to know not just the expected running time of an algorithm, but how likely it is to go over that critical time bound. Okay, and so we're going to introduce some tools to study that. And one way to study it is just sort of directly. Let's talk about the coupon collector problem again. Okay. So we said that the expectation in a number of rounds of coupon collection is order n log n. But what can we say about the probability that it is much larger? Okay. So suppose that we run for r rounds. And I want to argue that with high probability, I am finished collecting all my coupons. What sort of r do I need to set? Okay. So I'm going to show you a pretty typical analysis. And you'll get used to doing analyses this way. I wouldn't expect you to come up with this one right away on your own, but after you see this kind for a while, it will be natural. I claim that the probability that I missed coupon number k in these r rounds, right? Again, n coupons. What's the probability I never saw a particular coupon k? Yeah? Exactly. On any particular round, I have a 1 minus 1 over n chance of not seeing this coupon. And I'm making independent choices in each round, so I just take a product of all of those probabilities. Okay. And this lets me invoke my all-time favorite approximation. This is upper bounded by e to the minus r over n. Okay. We will be using over and over in this class these inequalities. Okay. So it decays exponentially in R. Okay. And this is n to the minus beta when R is beta n natural log of n rounds. Okay. Where beta is whatever constant you like. And this means that with high probability, we are done in order n log n rounds. We find coupon k. So remember, my definition of high probability is that you can make the probability into whatever small polynomial in n you want. Right? So the point is, whatever beta I want, I can change the constant in this O and argue that my probability of failure is smaller than that polynomial small bound. Yes? Okay. And this will also allow me to demonstrate why we use this definition of with high probability. Here, I've only talked about a particular coupon, k. But what I really care about is that I miss any coupon. Right? How do I get from the probability that I miss a particular coupon to the probability that I miss any coupon? Yes? Exactly. And this is one of the critical tricks. But within a week or two, we will have seen all of the probability tricks that we need in this class. The union bound is one that's used everywhere, right? So this is less than or equal. This is the probability of the union over all coupons of the probability that you miss that one. Right? And that is, by the union bound, less than the sum of the probability that you miss each one. Right? Which we've already bounded. Right? And they're all equal, so this is just n times the probability that you miss a particular one. Right? And so this is equal to n to the 1 minus beta. Right? And the reason with high probability is sort of a useful, robust definition is that I can say, well, if I have a bunch of events that occur with high probability, right, or that, then the union of those events also occurs with high probability. Right? If I have a polynomial number of bad possibilities, right, that are all polynomially small, then the union of those possibilities is still polynomially small. I can still make it whatever small polynomial I like. I just have to choose yet another constant in my asymptotic notation. Okay? So as we get used to this, I'm going to stop talking about the betas at all. And I'm just going to say, you know, n log n with high probability, and you'll know that you can fill in whatever beta you need to by setting the constants appropriately. And so this is a somewhat different statement from the expectation bounds. Right? It's not entirely stronger, right? But it's different, right? The expectation really sort of says just average over everything. It's going to be order n log n on the average. Right? What this says is that it's almost always going to be order n log n. So overall, that feels like a stronger statement. It's not quite stronger because it tells you nothing about what happens in the unusual case, right? This could still be true even if in the rare event that it fails, it suddenly took exponential time. Okay? Nevertheless, this is, for practical purposes, a much stronger statement. And in fact, it often is truly stronger because when this fails, you still get a polynomial worst case bound, and then that just gets swallowed up. And you can derive an expected bound from the high probability bound. Okay? But this is our first example of proving a high probability bound instead of an expectation bound. Is that clear to everybody? All right. Let me show you one more. Quite a similar approach. I should say, you can prove that this is tight. You can prove that there is no asymptotically smaller function for which the time is usually less than it. This is the best asymptotic bound you can achieve for coupon collection. So another one that I want to talk about is a famous problem called balls and bins. We're going to have several lectures pertinent to this. This is just a baby introduction. This arises in the study of load balancing, where you've got a bunch of stuff and you want to spread it out evenly. There are many ways to do this. If you've seen hashing, it's a canonical example of trying to spread things out evenly, right? We're going to talk for a moment about the specific case of n balls randomly thrown in n bins. Very classical problem. Pretty easy to see what the expected number of balls in a bin is, right? What is it? 1, right? Very easy. But what can we say about the maximum load? That's more interesting. And this is a case where it's actually easier to talk about high probability results than expectations. Like the way I know how to derive an expected maximum load is to give a high probability bound on the maximum load. Okay. So how do we do that? Well, we're asking about the max load, so what we want to show is that there is some k such that we are unlikely to see k balls in any bin. Let's start by thinking about a particular bin. You can already see that we're going to end up using the union bound at the end, right? So what is the probability that we get k balls in, let's just say bin 1, so I don't have to keep writing the word particular. This is basic probability you should know. Yeah?
It's going to be like 1 over n to the k, 1 minus 1 over n to n minus k to n choose k.
Exactly. This is a binomial distribution. Right? Generally represented this way, B of NP, where you are making you're flipping n coins that are biased with a probability p, and you want to count the number, you want the distribution of the number of heads, right? Here, we're just saying that a heads means it lands in bin 1, and a tails means it lands somewhere else. Yes? All right. I'm going to immediately simplify this. And then I'm going to use a bound that you should remember on binomial coefficients. Since we're talking about randomized algorithms, binomial coefficients pop up all the time. So you want to be familiar with them. And n choose k can be bounded by ne over k to the k. Now your n's cancel, and you're left with e over k to the kth power. Okay. And again, at least for small k, this is a reasonably tight bound. When does this get small enough? What do we want? What sort of value do we want it to have so that we can say that we're in the right ballpark? Well, we know we're going to be applying a union bound involving n different bins. So once again, we want to get this to be less than 1 over a polynomial, right? So what do we need to set k to be in order to make this like 1 over n or 1 over n squared or something like that? Well, if there were a constant in here, right, if this were like a half or something, what would we want k to be? Yeah, we would want to log n in the numerator, right? But this is actually a little bit better than that, because as we make k bigger, we're also making the denominator bigger, so we're getting a smaller value in the side. Yes?
I know I just talked about it. Wouldn't log n make it like it's e to log n, and that would be
1 over n. It would be 1 over e is what would matter, right? We need the denominator bigger than the numerator, right? And at that point, again, if this is any constant, then order log n up here will give you whatever polynomial you want, right? However, this is not a constant, it's actually shrinking, it turns out that what you can work it out. If you set k equal order log n over log n, gives you a probability of n to the minus order 1. In order to see that, when k is like this, your denominator is about log n. And so the first thing you do is raise it to the 1 over log n power. So you have a quantity that looks like this. And then you raise all of that to the log n power, right? And so this is a constant. And you then exponentiate the constant by log n, okay? So this is the number that works for balls and bins. You can say that with high probability, you have order log n over log n balls in bin 1. And now you can immediately also say, with high probability, you have order log n over log n balls in any bin by a union bound. Right? The point is that if you want the probability of failing here to be 1 over n squared, you just make the probability of failing here 1 over n cubed, and then you multiply by n for the union bound, just like we did in the coupon collector problem. Is that clear? Yes?
Can you just explain how exponentiation constant notification k and
Oh, well, so you need to focus on this part, right? That essentially, since e to the natural log of x is equal to x, it means that x to the 1 over the natural log of x is equal to e, right? And so when you set k to be equal to log n, what you're basically looking at is inside you'll have sort of log n over log n, right, the inverse of k. But then you raise that to a 1 over log n power. And that gives you a constant, which you then raise to a log n power. And that gives you your inverse polynomial. Okay. All right. Other questions? Yes? Correct. And so if you really want to be careful, you need to sort of sum this up. But notice that this is going to now shrink exponentially with k. So the sum up to more than k balls, right? Actually, I think this is a bound on the probability that there are more than k balls. So I mean, I could just start here. Or I can sum this over the larger values of k. Good catch. Okay. Any other questions? Okay. So we've now done a pair of exact analyses, and sometimes you really need to do an exact analysis, but it often means a lot more math and mess than is called for when you don't need that maximum tightness in your bounds. So we are going to next look at some techniques that let you give bounds on deviation more quickly because those bounds are often less tight. I should also mention, though, that we can conclude from this analysis that also the expected max load is order log n over log n. Can anybody see why that is? How do I get from this high probability bound to an expectation? Now I have to worry, right? Because, like, sure, it's small a lot of the time, but what about the exceptional cases where it's not small? What can I say about those? Yes, Bal. Exactly. Great. Yes. So basically, it's almost always log n over log log n. And then with a 1 over n cubed probability, it might be n. But that just contributes n times 1 over n cubed to the expectation. Just, you know, that's negligible. So from the tail bound, you get the expectation bound. I don't know how to get the expectation bound directly. There might be some cute trick with generating functions or something. But OK, so the next thing we're going to do is start looking at tail bounds. But it actually seems like a fine time for a break. So why don't we do that first? And then we can look at tail bounds with fresh eyes. Everybody just really wants to get back to lecturing, huh? I'll just sitting there waiting for me to start talking again. Yes? Sorry, what was that?
The bound that n is k is at most n times e divided by k of b is correct.
Yes, this is the probability of exactly k balls.
Yeah. And what I meant is the inequality used is not another bound of.
Oh, this is not a bound on the probability of at least k. That's what you're saying.
Just one.
Yeah. This is an upper bound of, yeah. So you need to take the sum over all the possible k's, but you use the exponential decrease. All right, let's get started now on tail bounds. And the whole idea of a tail bounds is that they let you make fewer, they pay attention to fewer details, which implies that you're generally doing less math, and that you get results that are less tight. But they're often good enough for what you want to do. Okay? So the granddaddy of all tail bounds is the Markov inequality. I'm moving through stuff now that I assume many of you know, so I will go quickly, but slow me down if something here doesn't make sense. The Markov inequality says that the probability that a given random variable is more than t times its expectation is at most 1 over t. If the random variable is a non-negative random variable. Okay? If your random variable can be negative, then the negatives can cancel out a lot of positive, and you can violate Markov. But if you have a non-negative random variable, you have this nice direct bound on the probability that the variable is large. It's harmonic bound. So let's see how we might apply this. So if we apply this to coupon collecting, we can say that the probability that you need more than beta n log n rounds is at most what? Well, for Markov inequality, all we need is to know the expectation of the random variable, right? What's the expectation in the coupon collecting problem? Yes? N log n, right? It's actually, we showed last time that it is h sub n, the nth harmonic number, which is bounded by n log n. And so n log n is an upper bound on the expectation, and so we immediately get 1 over beta from Markov's inequality, right? And we didn't have to do any math, right, beyond this. So it's a much easier bound to compute than everything we did over there. It's also a much weaker bound, right? We got 1 over beta where we know that the actual shape of the tail is an exponentially decreasing tail. Instead, we just have one that's harmonically decreasing. So a much weaker bound, but it's good enough for some applications. What can we say about balls and bins? What is the probability that the max load is bigger than some t? Yes. Correct. We can look at, we had a bound on the expected max load of log n over log n. And so we can just say that it's log n over t log n. But that was kind of cheating, because in order to derive this bound, we had to get a tight bound on the max load, and now we're using it to give a loose bound on the max load. If you just tried to use the Markov inequality from the start, it wouldn't work for balls and bins, right? Because what could you say, if you look at the basic balls and bins problem, what we said is that all we had was the expected load on a single bin is at most 1, right? And so we could use Markov inequality on the single bin to say that the probability that the load exceeds t is 1 over t. However, we then have to take a union bound over n different bins. And so in order to make that bound useful, we'd have to make t equal to n. So all Markov's inequality tells you is that the max load is at most n. And that doesn't help you very much with n balls and n bins, right? But let me show you another cool application of Markov's inequality. Going back to our complexity theory, I claimed that ZPP is equal to RP intersect co-RP. And now that we have Markov's inequality, we can actually formally prove that. Okay. So I'm going to take another board for this. So suppose we have a problem that is in RP intersect co-RP. What does that mean? It means that we have algorithm 1, which has no false rejects, sorry, no false accepts, and accepts with probability at least a half if it should. Yes? And co-RP means that there's another algorithm, algorithm 2, which never rejects if it is supposed to accept, and rejects with probability 1/2 if it should reject. Okay, so that's what we get from the assumption that the problem is in RP intersect co-RP. Can somebody describe for me a ZPP algorithm? Remember, ZPP has to always be correct. None of this probability 1/2 of accepting. Yes? Run both until the answers match. Why does that work? Great. And how long is this going to take? Yes. Good. Expected. So we want to know the number of times we're going to have to run both algorithms, right? So the first thing that we can say is that the probability that running both lets us stop is at least 1/2, right? Whichever of these two algorithms is the one that matters for this input, it has a 50% chance of giving the right answer. And if it gives the right answer, it will match the other algorithm, and we will stop. Okay? And that means that the expected number of tries, this is just a geometric distribution, is equal to 2. So in expectation, we'll need to run each algorithm twice. The two algorithms are, by assumption, polynomial time. So this is an expected polynomial time algorithm. So we have ZPP. Yes? Well, let's ask about the other direction. Now I have a ZPP algorithm. So how do I prove that I have how do I derive an RP algorithm? Right? So if this algorithm finishes, it gives the right answer. But it might take a long time. Right? In RP, I'm required to terminate in polynomial time. So how do I give an RP algorithm? Yes? Well, so what is that? What is the proper definition of too long here if we want to develop an RP algorithm? When should we stop? Yes? Exactly. We will just run for 2f of n time, right? If we get an answer, we use it, and it's the correct answer, right? Else, stop and reject, right? And thanks to Markov's inequality, the probability that we do stop and reject, that we run out of time, is at most 1/2. And that tells us that we have an RP algorithm. Okay, so that's a very simple use of a very simple tail bound that nevertheless has a quite meaningful consequence in complexity theory about the relationship between ZPP and RP. Any questions about that? No? All right. So Markov is the granddaddy tail-bound, which it's sort of accurate in two senses. It's sort of too old and weak to be useful for very much, but it has lots of descendants that are more powerful. So let's talk about the Chebyshev bound. So the Chebyshev bound requires knowing a little bit more about your distribution, right? The Markov inequality only cares about the mean, right? Which I will write as mu sub x, just so that I don't get it, so I don't have to deal with too many nested brackets. Okay. But the Chebyshev bound relies on the so-called variance, which is the expectation of how far the variable deviates from its mean. Okay. And of course, the square root of that expectation is known as the standard deviation. So I'm assuming you've all seen variance and standard deviation before. Quick reminder, why do we, if we're interested in kind of the deviation from expectation, why do we do this squaring? Why don't we just look at the expectation of x minus mu sub x? Right? Why do we do this square and then square root thing? When we could just look at the expected deviation. Yeah?
You don't want stuff canceling. You could have like something on a million, something on a negative a million, and then just like cancel.
Yeah, I mean, what's the value of this? What's this expectation? Yeah? It's 0, right? So that doesn't actually tell you anything, right? Because the deviations in the two directions cancel each other out. So you could take absolute values here, but they're a real nightmare to work with, right? We like having continuous differentiable functions, so we square it in order to make the deviations in both directions contribute. And then we take the square root to get back to the proper units of measure. Okay? So once you have these quantities, we can write down Chebyshev's bound, which says that the, where'd we go? Did I forget to write it down? Oh, there we go. So Chebyshev's bound is that the probability that the absolute deviation of x from its mean is bigger than t standard deviations is at most 1 over t squared. Okay. So Markov's inequality works in units of expectation and gives you a 1 over t. Chebyshev's bound works in units of standard deviation and gives you a 1 over t squared. Okay. And I won't take the time to do the derivation. You do this by applying the Markov inequality to the random variable x minus mu squared, right? X is a random variable. That means that x minus mu squared is a random variable, and also since it's squared, it's a non-negative random variable. And now you just plug in Markov's inequality, and this falls right out. Okay. So Chebyshev's bound is tighter. It's quadratic instead of linear. It requires you to know a little bit more, and requires you to calculate the standard deviations. But there's a very nice trick for calculating standard deviations that helps us a lot, which is that if we have a bunch of independent random variables, then their variances sum. So it's often very straightforward to compute a variance, and therefore straightforward to compute a standard deviation, and therefore straightforward to apply Chebyshev's bound. Okay. And this just comes from the fact that the expectation of this just comes from the fact that the sum of the xi's, that the sum of xi's squared turns into a sum of xi, xj terms. Yes? And when you put expectations around them, you get expectations of products. But when the different variables are independent of each other, the expectation of a product is the product of the expectations. And so everything works out very nicely and cancels out when you're computing the variance of the sum. Okay, again, I'm not going into detail on this because I believe you have seen this basic probability before. The math is worked out in the notes. Okay, so for example, let's talk about a binomial distribution. Okay, we have a coin that has its probability p. We flip it n times. We want to look at the number of heads that come out, right? And I'll call this variable x. So the expectation of x is very straightforward. It's just n times p thanks to linearity of expectation, right? But what can we do in terms of tail bounds? Okay. What can we do? Well, we need to compute the variance. Okay. So what can I say about the variance of x? Well, x is n coin flips. I can look at each of those coin flips as a single random variable, which is 0 or 1, and I'm just taking the sum of those n independent random variables, right? So in order to compute the variance of this binomial distribution, I just need to compute the variance of a single coin flip and add them up, right? So variance of one coin flip, that can be written as the expectation of the square of the coin flip minus the square of the expectation of the coin flip, standard formula for variance, right? So the expectation of the square of the coin flip, well, the coin flip is 1 with probability p and 0 otherwise. So here we have a p. And the expectation of the coin flip itself is p, so p squared. So we have p minus p squared, which is p times 1 minus p, is the variance of a single coin flip. That means that the variance of n coin flips is just n times that, because the coin flips are independent of one another. And that tells us that the standard deviation is equal to the square root of np times 1 minus p, okay. Which is order of the square root of n. And so, for example, if you're thinking about a fair coin, okay, 50-50 chance of heads and tails, Markov's inequality is not very useful, right? You can say that I expect half of my coin flips to be heads, and the probability that they're all heads is only a half. That's an incredibly sloppy bound, right? And you can't get anything useful out of Markov's inequality. Chebyshev's inequality, on the other hand, starts to bite as soon as you deviate by more than square root of n flips from or more than square root of n heads from the mean of n. So Chebyshev's inequality says that you will have sort of n plus or minus order root n heads if you flip an unbiased coin. Yes? And more generally, Chebyshev says that you're probably going to be within just a few standard deviations of the mean. Okay. All right. So Chebyshev's inequality is enough to actually develop some powerful algorithms. And it also uses very few assumptions so that it's very widely applicable. And I'm not going to have time to tell you the whole story of the algorithm today, but we can start. We're going to talk about a pretty simple problem, median finding. I know that you are all intimately familiar with this problem because you had to do it for your problem set, right? And you worked on a problem that, so pick a random pivot and take things on one side of the pivot until you home in on the element that you're looking for. Yes? Did I not put that on your problem set? It's kth largest, right? So the point is that median is a special case of kth largest, right? I'm going to focus on median, although actually everything that I'm saying is going to be applicable to finding the kth largest for any k. Okay? So you explored this algorithm, which is like a quicksort equivalent, but for finding a median instead of sorting the whole list, right? And you solved it in order n time in expectation. There's also, you probably studied in your basic algorithms class, a deterministic median finding algorithm that runs in order n time. But now let me ask what is a very unusual question for theoreticians. What is the constant? Right? Once you're down to order n, there's not much more you can improve besides thinking about what is the constant on the n. Right? And like that deterministic algorithm that you study in basic algorithms classes has a pretty poor constant. I forget if it's 7 or 8 or something pretty large. This one, what you did was an algorithm called quick select, variant on quicksort. Quick select. It has a running time, I think, of like 3 point something n, if I remember correctly. There's also a pretty interesting theorem that says no deterministic algorithm can beat 2 minus some tiny epsilon n comparisons. Okay. But I am going to show you that with a simple randomized algorithm, we can do much better than 2. Okay. Sorry, 2 plus epsilon n. You can't beat 2. And they've been working on pushing up this epsilon, but it's still pretty small. The randomized algorithm that we're going to use applies, and this, by the way, was developed by Floyd and Revest. Revest is, his office is right over mine in this building. So we are going to explore a random sampling technique. And what's the idea behind random sampling? The general idea behind random sampling is that you have something big, and you want to understand something about it without looking at it all, because it's too expensive to look at it all. And that's sort of a very powerful intuition for developing randomized algorithms, is I don't want to look at everything, figure out some way to learn something without looking at everything. And what is often a powerful way to learn something is by taking a small random sample and analyzing the small random sample. Right? If I want to know the fraction of Republicans and Democrats at MIT, I just will need to, send people out into the dorms, into random places in the dorms, ask who they meet, what their political affiliation is, and the fractions that I get back will tell me something about the distribution of Republicans and Democrats in the entire student population, right? So you can apply the same idea to many algorithmic problems, and the question is, if we, what kind of random sample is natural here, and what might it tell us about the median that we're looking for? Well, if you're talking about a set of elements, it's pretty obvious what a random sample should be, right? I can choose a bunch of elements at random. The question is, what will that random set of elements tell me about the median? Will the median be in the random set? Well, almost certainly not, right? I'm not going to be that lucky. So what can I learn from the random set that might tell me something about the median? So I'm going to assume that I'm going to look at my list as ordered just so that I can think about it, okay, even though I don't actually have a sorted list. And I'm going to imagine taking a random sample. So I'm going to get a few items. Okay. What might I learn by looking at that subset of the items? Yes? Okay, so I could think about taking averages of numbers, but if you think about it, median is not dependent on the values. It's only dependent on the order, right? So averaging the numbers shouldn't be necessary. It's only the order of things that matters. Yes? Great. So the first intuition is that the median of this set is going to be close to the median of the entire set. But what does close mean? And how can we use that? And get something even closer to the median. Although you still would have to be really lucky in order to get the median itself, right? So we're never, like, taking these small samples will never give us the median, right? At some point, we're going to have to use our information and go hunting through the entire set, because that's the only way we're going to find the actual median, right? But the question is what information we can use to reduce the effort that we have to invest in the entire set. And so the insight here is not trivial, because it doesn't work to just look at the median. But what Floyd and Revest said is, I'm going to give you some numbers here, and we'll sort of do the analysis next time. Okay? They sort of said, take, let's see, what would be a good number? I think n to the 3/4. Yeah. Take about n to the 3/4 elements in your sample. So this is, I mean, this is a very small fraction of the set, right? A negligible fraction of the set. Okay. Their insight is that sort of intuitively, the spacing of elements in your sample is going to be about n to the 1/4 apart, right? There's going to be about n to the 1/4 elements in the full set between each pair of adjacent elements in the sample. This is only an intuition, right? But there's going to be a gap of about n to the 1/4 here. Okay. So what that means is that if you look at about n to the 1/2 of, you look at the middle n to the 1/2 range of this n to the 3/4 elements, okay? It's going to span about n to the 3/4 of the elements in the original set. And more importantly, it's going to contain the median in that span. Okay? In other words, if you look a little to the left of the sample median and a little to the right of the sample median, you'll be able to get an element that is smaller than the true median, and you'll be able to get an element that is larger than the true median. Okay? And the amount of error is going to be driven by that by the standard deviation of this sampling process. Okay? So what you do is you choose this random sample. You extract a near upper and near lower bound on the true median. Okay? By looking a little below half of the sampled set, oh, I should say, you sort the sample set. Right? This is only n to the 3/4 elements, so sorting it is free. It is effectively free. Okay? So then you look a little bit to the left of the sample median, a little bit to the right of the sample median, and that gives you something which is below the real median and something which is above the real median. Okay? Having done so, you now scan all of the items. counting and discarding those outside the two bounds. Yes? But it's only 2n comparisons, right? It's not 2 plus epsilon n comparisons. I'm going to actually make it a lot better than that, but I'm going to save that for next time so we have a fun discovery next time as well. Okay, but for now, I'm going to show you that we can get 2, right? 2 plus little o of n, right? So I do this scanning, and I can count how many items are to the left of the lower bound, how many items are to the right of the upper bound, and how many items land in the middle. And it's going to be about n to the 3/4 items landing between these two bounds. Okay? At that point, I will just sort the stuff that landed in the middle and count however like a certain number of items are smaller than the lower bound. That tells me how far I need to seek through the sorted stuff in the middle, and that gives me the median. Okay? So the overall cost of this is 2n plus little o of n, which is strictly better than what any deterministic algorithm can achieve. Okay? Now, we still have to do all the math, which I will take care of on Monday. And one of your homework problems may need to wait until that math is done. Okay. I should also say that when I do the math, I will show you how we can improve this to 3/2. So you can think about that over the weekend, is how to get dramatically better than the 2n comparisons of a deterministic algorithm. Yes, a question?
Like, I know it's probably like is this guaranteed work? Like, did you ever get the bounds to like?
No, this is not guaranteed to work, right? This is a Las Vegas algorithm, right? Or sorry, actually the way it's designed, it's actually a Monte Carlo algorithm, right? We will show that there is a high probability of finding the median between your two bounds, but there's a small chance that you don't. And then you have to go off and do something else, right? But the probability of that is going to be very small, and so taking a long time to find the median a different way won't, I mean, we can turn this into a Las Vegas algorithm, right? It's one that will be fast with high probability, and if it fails, we'll just run a slow median finding algorithm, and that won't matter because it's very unlikely to happen. Okay? Other questions? Yes? Yes, that's right. That's how you get the 3/2. Yes?
Wait, how do you do that stuff where you like extracting your algorithm?
So I will fill in the details of that next time. Essentially, after sorting this sample, you take something which is a little bit smaller, a few indexes smaller than the middle element, and a few indexes bigger than the middle element. And I will prove to you next time that between those two elements, you will find the actual median with reasonable probability. Okay? Other questions? All right, I'll see you on Monday.